So what's actually happening during a phase change? Where's the energy coming? Where is it going? What are the different phase changes called? How are these things all interrelated? And this is one thing we need to discuss. First, let's look at some kinetic energy distribution curves. What's shown here, the graph here, is the distribution of thermal energy. We see on the x-axis, we have your kinetic energy, and on the y-axis, the fraction of molecules. We have two different particles shown here, a blue line and a red line, and the blue is showing lower temperature, and the red is showing higher temperature. So it's the same exact particle, but what it's showing is the distribution of the particles and the energy they have at two varying temperatures, okay? Temperature itself is a measure of the average kinetic energy. Remember what average kinetic energy is? We talked about this previously. We can measure it, or we can calculate it. E sub k is 3/2 RT. So temperature is a measure of the average kinetic energy. At any temperature, there are always some particles at the surface that have enough energy to escape the attractive forces of liquid to become a gas. Like these water molecules here that are escaping the liquid to go into the gas phase. Again, that is what a vapor is, forming the gas phase particle before I've reached the boiling point of the system. The larger the surface area, the faster the rate of evaporation. So a larger surface area, these particles are able to escape faster. Because if I have a larger surface area, I have more particles at the surface, hence more are going to escape. As the temperature increases, the fraction of molecules with sufficient energy to escape also increases. As I put more heat into it, as I increase the temperature, that's putting more heat into the system, right? So I'm putting more heat in, that's breaking up those IMFs between the molecules, or those attractive forces between the molecules, allowing those molecules to actually escape the system entirely. And so the graph down here is showing you just that. This is the same particle under two different temperature curves, the lower temperature and the higher temperature. And then the fraction of molecules, how many molecules do I have? I see under the lower temperature, the bulk of my particles are over here. At higher temperature, the bulk of my particles are over here. Higher temperature, more particles have higher kinetic energy. Again, makes sense, right? Kinetic energy is due to temperature. Or we can calculate the kinetic energy based on the temperature. But this line, this dashed line we see here, is the minimum energy required for the particles to escape. They have to reach at least that energy to be able to escape the system. So what we see underneath here, this blue portion under here is a little bit of the particles escaping. We see the red has over double that amount of particles escaping. So higher temperature, more particles are able to escape. None of this probably surprises us. How can we apply this? Well, let's look at this example here. In each figure, the dashed line represents the threshold kinetic energy required to vaporize the liquid. Both substances are at the same temperature. Which substance has the strongest IMFs? So this is the line required for vaporization. When I compare these two lines, I see that the area underneath the curve beyond the line for B is a lot greater than A. That means a lot more particles have escaped. Here, fewer particles escape. The question tells us that both substances are at the same temperature. So that means the only difference here is IMFs. Will the weaker IMF allow the substance to escape easier, or will the stronger IMF allow the substance to escape easier? It's the weaker IMF, right? The more particles escaping, that means that this system has weaker IMFs, which means this one is stronger. They're not, in fact, equal, and substance A wins. Okay, you do need to know the names of the different types of phase changes we have, and you also need to understand if they are endo or exothermic. And we're going to show it graphically, but we're also going to talk about them by definition. First, let's talk about their definition. Evaporation is when a liquid goes to the vapor phase at any temperature. It doesn't have to be at the boiling point. If a liquid is going to the vapor phase, it is evaporating. Vaporization is the liquid going to gas at boiling point. So if I'm vaporizing something, I am boiling it. Evaporation, again, any liquid escaping to the gas phase at any point, any temperature. But vaporization specifically is the liquid going to the gas phase at its boiling point. And again, remember, boiling point is dependent upon atmospheric pressure. Condensation is the reverse of this process. It's the gas going to the liquid at the boiling point or condensation point. So gas to liquid, condensation, liquid to gas, vaporization. Just a quick reviews here of your boiling point and normal boiling point. Again, boiling point, the temperature when the vapor pressure is equal to atmospheric pressure. And normal boiling point, the temperature when the vapor pressure is equal to standard atmospheric pressure, which is 1 atmosphere, which you will see written as 760 millimeters of mercury, 760 torr, etc. You can convert that into units of PSI, kilopascals, inches of mercury, whatever you may need. The next phase change we're going to talk about is the difference between solids and liquids. Fusion and melting mean the same thing. I don't care if you call it fusion or if you call it melting. Fusion and melting is solid going to liquid phase. Solidification, crystallization, and freezing are liquid to solid phase. I don't care which one you use, they all mean the same thing. But again, fusion or melting is solid to liquid, whereas solidification, crystallization, or freezing is liquid to solid. Your melting and freezing point is the temperature with the vapor pressures of the solid and liquid are equal. So I've now reached that same kind of concept as the boiling point, except this case, it's the solid and liquid vapor pressures that are equalized. Sublimation and deposition is going between the gas and solid phases. So if something is being sublimated, it is going straight from solid phase to gas phase. It is completely skipping its liquid phase. If something is being deposited, it's going from the gas phase down to the solid phase, completely skipping the liquid phase in between. And then I know I've talked about this already, but just reminding you guys, pure substances boil and condense at the same temperature. Pure substances melt and freeze at the same temperature. That's why water both melts and freezes at 0 degrees C and boils and condenses at 100 degrees Celsius. And here's how you can see these graphically. You do need to know the names for these phase changes and know whether they're endo or exothermic, but sometimes putting on a graph can help a little bit. Remember, H is your enthalpy. So as I'm going up, it's increasing. That means the up process is endothermic. The negative delta H is exothermic. Solid to liquid, liquid to gas, or solid to gas. So fusion, vaporization, and sublimation are all endothermic processes. Condensation, freezing, and deposition, or your gas going to liquid, gas going to solid, or liquid going to solid are all exothermic processes. Because in order to freeze something, I have to take its heat away. Remember, this is always talking about the transfer of the heat itself. So if I'm freezing something, I'm taking its heat away. It's an exothermic process. And we're going to be using these values very soon, but delta H vaporization, the heat of vaporization, is defined as the enthalpy change when 1 mole of pure substance is vaporized. Delta H of fusion, heat of fusion is defined as the enthalpy change when 1 mole of a pure solid melts. And you are responsible for these definitions. And again, being able to remember if they're endo or exothermic, putting them on the graph, etc.